Hi everyone. So this is the eighth week of the interaction session on the course on robotics basics and selected advanced concepts. Uh, I'm your TA for this course. Just a brief introduction. My name is Soumya and I am a PhD scholar at IIT Gandhinagar. I work in the field of robotics. Okay. So it has been a couple of weeks and this is the eighth week. So I hope you remember what all was covered in the last class. Though we have very like less relation between what was covered. Like we learned about redundancy and how do we resolve redundancy in human arm and what are hyper redundant robots, and we dealt with a lot of definitions and a lot of questions, right? All of you were able to answer it correctly. So in case you were absent, I request you to go through the YouTube lecture that is already uploaded on my channel. Okay. We also read about flexible robots and how we do have different modeling techniques, or how do we find the solution for all those robots which are infinite dimensional systems. Okay. Before that, so this was something that we did last time, but before that, we read about Jacobians, serial manipulators, and parallel manipulator, both of their Jacobians, and what are singularities. How do we go for statics? Before statics, we had read a lot about kinematics. Now, it was for serial robots independently, and then it was for parallel robots as well. For serial robots, it was direct and inverse kinematics, and we saw that how inverse kinematics is a bit difficult when we talk about serial robots, whereas it is opposite in the case of parallel robots, right? All of this we had already discussed. So after that, we this time we are going to deal with dynamics of serial and parallel robots, and you might already know that there are some methods to solve the dynamics of these robots, not robots, dynamics in general. And you can either go with Newton's laws of motion, or you can also go with Lagrangian formulation, right? And there is another approach that we'll talk. Okay, so I think you've gone through the lecture and you're already aware of these things. So the basic thing is that we'll start with Lagrangian formulation, and then we'll see how do we derive the equation of motion from those Lagrangian formulations. Then what are inverse dynamics, and so the difference between direct, so you know already what is direct kinematics and what is inverse kinematics, right? The difference here is also the same, except it is dynamics. The force and torque are here coming into picture. Here they all are coming into picture. So there only velocities were involved, right? There was no component of force and acceleration coming over there, but here we have forces and torques into the picture. All right, so we are more now concerned about what are the joint torques. So if we talk about inverse kinematics, it's like if you want to follow a certain trajectory using the end effector, what should be the joint torque that we are providing at the joints. All right, so it's just instead of kinematics, we now have dynamics. Okay, and then today we'll see the inverse dynamics and recursive formulation of dynamics of manipulators. So all of these will be seen. So I hope you have already gone through the lecture, and it should be a smooth process if you've gone through. And in the next class, we'll have motion planning and linear control. So we'll see in the next class itself. So it would be a little pivot, but we'll see. And I hope so. Can I have a show of hands? How many of you read control systems? Like you are familiar with the course on control systems? No one. So is your background electrical, or is it some other branch? Because when we'll be talking about control system, there will be a lot of controllers coming into picture, and how why do we use the controllers, and why do we want to control the motor speed, everything, all of those things, motor torque, all of these things will be coming. So may I know if you have some background in control system? can just type in the chat box, it's okay. Okay, so I'm not getting any replies. I hope I am audible and my presentation is visible. Can you guys reply at least for this? Because now I feel that my voice. Okay. Okay, open loop and closed loop you're aware of. Okay, that's fine. So if you're aware of all those things, I think it would be really helpful. And if you read about PID controllers, that is also good, because when we do linear control, we mostly use PID controllers. So it would be good if you have some background in control. Okay. Okay. So, okay, coming back to the lecture. Yeah, so today we are going to deal with just dynamics of serial and parallel robots, all right? Okay, so let's have a recap of what was taught. So just let me write the heading. Okay, so what are robot dynamics? So in robotics, we mainly study, sorry, we mainly study two things, or we study actually three things. Kinematics we have already seen, statics we saw in the last class, and the other is dynamics. So this is the part that we'll be covering today. Okay, so what does kinematics mean? It means that we consider the motion without considering forces, right? So for example, position of robot end effector, or uh, velocity of the robot joints, or acceleration of links. So kinematics basically, or not acceleration, it's basically the velocity and position. So kinematics answers questions like where is the robot or how fast is it moving. That's it. It does not explain why the robot moves. Okay, so this is missing in kinematics. Okay, but in dynamics we are actually interested in studying the motion caused by forces and torques. Okay, so in robotics dynamics we answer what torques should motor apply, or what forces act on the robot links, or how do mass and inertia influence the motion. So all of these things come into picture. So basically dynamics studies motion of the robot links caused by external forces and torques. Okay, they are very important. So in most one of the assumptions that we need to consider is the following. uh, all robot links are rigid bodies, unlike the flexible ones that we saw in the last class. Okay, all of the robot links are rigid bodies. This means that we don't have any deformation, we don't have any elasticity, yeah, and geometry does not change during the motion. Geometry change is not there. Okay, so this simplifies the analysis. So there are some methods for deriving robot dynamics, and from here this is really important. this. Yeah. So the first method is Newton-Euler method. Okay. So this is based on classical mechanics. What does this mean? What do we do in this? Can someone tell me the steps that we follow when we use Newton-Euler method? Like steps or the equations, anything that you're aware of? Like Newton-Euler method is the simplest method of all. Everything that we do that you have been learning since class 9th actually comes into picture here. So what all it is? So you might be aware of free body diagram, right? So the very first thing that we do is draw free body diagram of each link. Okay. And then we apply Newton's second law. What it is? Mass into acceleration. And then we apply Euler's rotation equation. And it is torque is equal to I alpha. Okay. So what are the advantages of this method? This is important. It is very physically intuitive. And it is efficient for recursive algorithms. Okay. The one of the disadvantages that we can say about this method is that it requires many vector calculations. Okay. The second method, so this Newton-Euler method was the first method. Let's talk about the second method. The second method is Lagrangian formulation. And what does it say? It is basically energy-based formulation. Can anyone tell me what is officially the definition of Lagrangian? Like how it is defined as a combination of energy? Sorry. Does anyone remember from the lecture? How do we define this? Okay. So it's basically energy based formulation, right? So what do we do? Instead of forces, we use kinetic energy and we also use potential energy, and then we derive the equations using calculus. So the advantages of this are it has compact equations, okay, and it is easy for symbolic derivations. It's clean. Okay. So after this we also have third method, which is Keynes method. Okay. And this is the most advanced formulation used for complex system. So the main uses that we won't go into details, but the main uses that we have are generalized speeds and generalized forces. It is often used in multi-body dynamics software. Okay. So there are two fundamental problems in robot dynamics: direct dynamics and inverse dynamics. Okay. So okay, I should write this. Which we also call forward dynamics. Okay. So what happens in this? And the second one is inverse dynamics. See this later. So what happens in direct dynamics? In direct dynamics, you are given the robot structure, that how does the robot look like, that is actually common thing. And how does the robot look like what are the joint positions and everything, and what are the applied joint torques. Okay. So what you're supposed to do, you're supposed to find the joint motion. So given the torque of the motors, you are supposed to find out what is the motion of the joints. So this basically requires solving differential equations. Okay, it is used in physics engines normally, or any simulation animation. Okay, what happens in inverse dynamics? So in inverse dynamics, you have some desired trajectory given. Okay, and which are, let's say, q dot t, q double dot t. And then what are you supposed to do? You're supposed to find out what are the required torques. Okay, so why are they used? What is the utility of doing this? This is used in control, motor sizing, if we want, like what should be the capacity of the motor, and for trajectory planning. Let's say I want to go from this location to this location. What should be the joint torque that should be applied at the joints? Okay, so all of these. Just hold on. Okay. So this is the basic. Okay. Now this is the basic difference between this in direct and inverse dynamics. Now let's move to mass and inertia of a lake. Okay. So before deriving dynamics, we must understand mass distribution. So what is the mass of rigid body? How do we define the mass of a rigid body? So mass is defined by integrating the density over volume, right? This is the definition of mass, where rho is the density and V is the, or I should not write so, V is the volume. Okay. Then let's talk about inertia. What does inertia represent? It represents resistance to motion. Oh, sorry, resistance to rotation. Okay. So for 3D bodies, we define inertia tensor. And what is inertia tensor? It is given by I, which is Ixx, Iyy, Izz. Here it is Ixy, Ixz, Ixy, Iyz, Ixz, Iyz. Okay, so the matrix describes how mass is distributed. And what are the elements of inertia tensor? So your Ixx is integral of y square plus z square rho dv, Iyy x square plus z square rho dv, Izz x square plus y square rho dv. So these are the moments of inertia. Okay, and let's talk about the product of inertia. How do we define it? So your Ixy is negative of xy rho dv, Ixz is xz rho dv, and Iyz is yz rho dv. Okay, so there are a few properties of this inertia tensor, that it is symmetric. Okay, so Ixy is equal to Iyx. Okay, secondly, eigenvalues are the principal moments of inertia. Okay, and then eigenvectors define principal axes. Okay, now we will now move to Lagrangian formulation. Okay, so this is the main concept. So the first step that we are going to recap is kinetic energy. So the kinetic energy of a rigid link has two components. The first one is translational kinetic energy, and the second one is rotational kinetic energy. So this is the motion of center of mass, half m vc square, center of mass will c. And for rotational kinetic energy, it is rotation about the center of mass, and it is half omega transpose I omega, right? So the total kinetic energy of, let's say, some link I is what? It is KEI is half MI VCI square plus half omega I transpose I omega I. Okay, now let's talk about potential energy. Okay, so for robots we usually consider gravity only, So your potential energy of some link I is minus MIG transpose P into, PCI. Okay, are these? This PCI is position of center of mass of that link, and G is the gravity vector. Okay, in the third step, what do? We define the Lagrangian. Okay, so your Lagrangian is kinetic energy minus potential energy. So for an N-link robot, your Lagrangian is summation of I from 1 to N, kinetic energy minus potential energy. Okay, now let's write Euler-Lagrange equation. Okay, so for each joint coordinate qi, d by dt of dou L upon dou qi dot minus dou L upon dou qi is equal to qi. What is qi here? Qi is the generalized force. Okay, so for robots, generally qi is equal to ti. Okay, the torque. So your final robot dynamic equation is what? It is m q double dot plus c q dot into q dot plus gq is equal to tau. What are these terms? This is your mass matrix. Okay, it depends on the robot configuration, the symmetry, and it is always positive definite. This complete term represents Coriolis and centripetal term. Okay, these basically represents velocity dependent forces and coupling between the joints. This is gravity vector. It represents gravitational torque. All right, so this is the final equation of motion of a robot. Okay, let's see an example. So let's take an, yeah,
Q double dot.
hold on. Just a second. I'm coming to your question. I'm checking if I've missed something, but okay. Yeah, you can ask what about Q?
Ma'am, what is Q double dot?
Okay, what is Q double dot? So, you have states of your robot. These states of the robots can be X, Y, Z, phi, theta, psi, etc. So this q dot is basically the double dot of these this vector. Okay, So it's acceleration term. If I say x double dot, it is acceleration, linear acceleration in x direction, y double dot in y direction, etc. Phi double dot is what is your angular acceleration. Okay.
Okay, ma'am.
Yeah. So, okay, let's go with the example. So, uh, an example we can take uh, this planar 2R manipulator. So let's say your manipulator is like this. It has an effector here. This is theta 1 and this is theta 2. Okay, let's say this link is L1 and this link is L2. And the mass, corresponding masses are M1 and M2. Okay, so the robot parameters that we have here are basically theta 1 and theta 2 because they comprise the joints. What are the link parameters? M1, M2 are the masses, L1, L2 are the lengths. Okay, center of gravity distance is R1 and R2 and inertia is I1 and I2. Okay, center of gravity means this point and this point. What is the vector corresponding to it? Okay, so we'll talk about it. Just let's move forward. So your angular velocities, first we'll talk about the angular velocities in detail. So for link 1, it is omega 1 which is equal to theta 1 dot, right? For link 2, your omega 2 would be what? Would it just depend on theta 2 dot or would it be a combination of theta 1 and theta 2?
Ma'am, combination of theta 1 and theta 2.
Right, very good. So it would be a combination of theta 1 and theta 2. So because this is not independent, it depends on the movement of the first link as well. So it has to be a combination of both of them. Okay. Now, so once you know about these angular velocities, and if you calculate the linear velocity, so what would be the linear velocity for link 1? It would be Vc1 is equal to, let's say, r1 into theta dot, theta 1 dot. So in similar way, we can calculate for link 2. If we know the linear velocity and if we know the angular velocity, we can write that the expression for kinetic energy. Similarly, uh, if we know the potential energy of the system, like at what height it is from the uh, ground, then we can write the expression for potential energy. I'm not going into derivation in the interest of time because we have to do a number of questions. But the thing is, and this is already derived in the lecture, it's just I'm repeating the steps. So you write the kinetic energy, you write the potential energy, and after that you do Lagrangian is equal to kinetic energy into minus potential energy. Then after this you can calculate del L upon del theta I because we were calculating with respect to Q. Q here is theta 1 and theta 2. So you have to do it with respect to theta 1 and with respect to theta 2. You insert everything, you take t by dt, whatever we saw, how do we define. So basically this equation. This is very important equation. Okay. You are supposed to calculate this. Once you calculate all of these things, then after this you can just get the final dynamics equation of motion for this 2R manipulator. So it is just that you have to have formulate this Lagrangian, and once you formulate this Lagrangian you have to plug it into the equation of motion. You'll be able to get two equations of motion because this is about two links. So tau 1 is equal to something and tau 2 is equal to something. Okay, and it would basically be mass matrix into your states plus Coriolis term plus gravity term. Okay, so if I write the equation directly, though I'm not deriving, so your torque would be for the first joint would be m11 theta 1 double dot plus m12 theta 2 double dot plus h1 plus g1. Okay, your torque 2 would be m21 theta 1 double dot plus m22 theta 2 double dot plus h2 plus g2. So basically this term m1 m2 can be written in the form of a matrix, right? 2 cross 2 matrix. It is just expanded over here. So this is your mass matrix, this is the Coriolis term, and this is the gravity term. Okay, when we do inverse kinematics, so we basically try to compute the torque for robot control and actuator design. All of these things are there. Okay, now if you want to simulate, if you want to simulate robot dynamics, then how would you do it? Like we already know, and this is very important, the equation of motion, uh, mq double dot plus c, which is a function of q and q dot both, into q dot plus gq. So if you rearrange from here, you'll get q dot to be equal to, just take m inverse multiply by m inverse on both the sides, m inverse q into torque minus c minus g. Okay, now so we need to solve for this. Apart from this, we need to convert to state space. So we need to define space vector, which is x, which constitutes of q1, q2, and up until qn, and then maybe q1 dot, because we need velocities as well as in the state, as well in the states, q2 dot up until qn dot. So in this way we can write x dot is equal to g as a function of x and tau. Okay, so you can easily solve this equation of motion using, if you use MATLAB, your ODE 45 is best for solving these integrations, and Runge-Kutta methods are also good. Okay, if your equations are stiff, that means that they are separated by order of 10 to the power 3 or so time constants, then the equations become stiff and ODE 45 does not work. You have to go for stiffer versions of these ODE solvers. I think it is ODE 23s. Just confirm this. I think this was one of them. Okay, so this helps in robot simulation and trajectory prediction, etc. So I hope this is clear. So just a brief of this equation is really important. The this equation particularly is very important because it has inertia matrix, Coriolis and centripetal forces and all, gravity terms and whatever actuator force are there. So all robot controllers are built using this equation. All robot controllers are built using this equation. Okay, then okay, I think I'm just looking at the slides if I've missed something. Okay, so does I just have a question that I want to ask. Does the mass matrix depend on configuration? You have inertia terms, right? All of them, and all of them are defined. So do you think they depend on the configuration? I don't know, you can just think any answer is correct. So you can tell me. Okay, so can you tell me uh, if you are holding a if you go to gym and you're holding a dumbbell, if you hold it close to body, are you able to lift it easily? Or if your arms are stretched, then you are able to lift it easily. Which gives you easier lift?
Close to body, easier lift.
Right. Close to body has easier lift. That means your M matrix, which is inertia matrix, depends on the joint configuration. Okay, if your, let's say your arm is folded, it is easier to rotate the arm and you see that it requires less effort. But if your arm is fully stretched and you're going to do the same motion, it is a bit harder. Okay, so your joint configuration actually plays a major role, uh, your inertia matrix, which depends on the joint configuration, plays a major role, and it depends on the configuration, and it makes the task either easy or difficult. Okay, so the other question is, as we talked about, uh, like for example, if there is a torque at some joint, so does one torque depend only on that joint? No. In the robots, any torque can depend on combination of joints. For example, links are connected rigid bodies, so motion of one link changes inertia of the others. For example, if there is a double pendulum, so all the joints do affect each other, and they shouldn't be dealt independently. Okay, what are Coriolis forces that we talked about, the C matrix? So uh, okay, if you walk inside a moving train, you feel the force sideways, right? That is a Coriolis force. Or if you have seen the western commodes that we have, so when people flush, okay, what happens? The water inside it moves in a particular direction, but it is different in case of northern hemisphere and southern hemisphere. For example, you go to some other part of the world, the direction of the spin is different as compared to what we see in India, and that is a result of Coriolis force, and Coriolis force is not in the same direction in the northern hemisphere and southern hemisphere of the earth. So Coriolis force is basically all the centripetal and centrifugal forces coming into the picture. All right. Okay. So in robots, the joint velocities interact with other joints. For example, if one joint rotates fast, joint 2 experiences extra torque, and all of these things happen. And here we have the Coriolis force coming into picture. Okay. The mass matrix, the M matrix that we saw, is symmetric, right? So when we write the kinetic energy, what do we write? We write half into Q dot G into MQ into Q dot, because energy must be real and positive. If the matrix was not symmetric, energy could become imaginary. Therefore, mass matrix needs to be symmetric. All right. Okay. Why does this Lagrangian formulation that we did does not include friction? Like, if you are supposed to include friction, how would you do it? So Lagrangian mechanics basically describes conservative systems. So energy conserving systems. Friction basically dissipates the energy, so we add it manually. Okay. So instead of having special term, what we usually do is, we know this already, right? Q double dot plus CQ and Q dot ka function into Q dot plus GQ. We add an additional term of for friction over here, where this can just be a damping term, some damping term. It can be viscous and it can be Coulomb friction or whatever. So we add friction in this way, or if there is any other contact force, any dissipating force, okay, any dissipation of energy that is happening can be accounted in here. Okay. And let's say if we are going to use operate our robot in space and then there is no gravity over there, you just have to omit this term. Okay, so these are valid for space robots. Oh, okay. So now I just have a subjective question and then we'll move to, or should I take the subjective question at the end? No, let's take it now itself and then we'll move to the objective ones. Okay, or maybe, okay, I'll give some hints about this question. I'll not discuss the complete question in detail and you're supposed to do it. Okay, so what I'm saying is we want to derive, please note down this question, and I'll be giving some hint. It would be good if you solve it right away. Derive the equations of motion of a PR planar robot. Okay. So the first joint is a prismatic joint and it moves along the x-axis. Let me draw it first, then it would be much more clear. So this is a prismatic joint with mass of m1, okay, and it moves along this x-axis. It is at some distance d currently, and it carries a link, okay, and this link is at an angle of theta 2. Let's say the end effector position is x comma y, and it has m2, i2, l2, r2, okay, and the torque that is being applied is tau 2 in this direction. In this direction it's linear force and it is F1. So a force F1 acts along link 1, okay, whose mass is m1, and the translation of m1 is denoted by d1. Okay, the second link rotates by theta 2 and its mass I, there is a mass and I is the component of inertia, and location of center of mass is denoted, all of them are denoted by m2, i2 and r2 respectively. Gravity acts along the negative y axis. You're supposed to derive the equation of motion for the system. Alright, so I hope all of you have taken or noted down the question or written all of these things. So what is the generalized coordinate vector? What would be q in this case? So let's start with this. Okay, so we are going to derive the equation of motions. So your generalized coordinates oh, just a sec. Yeah, so your generalized, so the robot has two joints basically, right? One is prismatic and the other is revolute. These two joints we have. Prismatic is basically the displacement along x-axis, which is d, and for revolute joint we have theta 2, right? So the vector is d and theta 2. All right, now external generalized forces, if we are talking about the forces, what are they? Q is F1 and tau 1, because these are the forces that are being applied. F1 is the force acting on the prismatic joint and tau 2 is the torque at revolute joint. Okay, so where are the positions of center of masses? Where are their positions? So let's talk about link 1. For link 1, the prismatic joint moves along x, right? So position of mass m1, x1 is equal to d and y1 is equal to 0, right? If we talk about link 2, the base of the link 2 is located at d comma 0. Yeah, so the center of mass of link 2 is located at a distance r2 along the link. Okay, so what would be x2 in normal coordinate case? It would be d horizontal distance plus r2 cos theta 2. And what would be y2? What is the position of center of mass of the link? It is r2 sine theta 2. I hope all of this is clear from the figure, right? There shouldn't be any confusion. So when we know the position of center of mass, let's find what are the velocities. We can differentiate with respect to time. So we'll differentiate the equations that we have written here, these both and these both. So what is x1 dot? It's d dot. Let's keep it a generalized vector, not d1 and just d. Okay. And what is x2 dot? Oh, sorry, y1 dot? It's again 0. Okay. So what is the velocity magnitude? Velocity magnitude is v1 square is equal to d dot square. Okay. So it's just being satisfied. Now let's talk about link 2. So for link 2, again we'll differentiate this equation. x2 dot is equal to d dot minus r2 sine theta 2 dot, sorry, theta 2 into theta 2 dot. And y2 dot is equal to r2 cos theta 2 into theta 2 dot. Right. So what is your v2 square? It is d dot minus r2 sine theta 2 into theta 2 dot ka square plus r2 into cos theta 2 into theta 2 dot ka square. Okay, you can just simplify this and what you'll eventually get is I am writing d dot square plus r2 square theta 2 dot square minus 2r2 d dot sine theta 2 dot. This is something that you can calculate. Okay, you'll be able to do it. It's just a simplification. Okay, now let's talk about the kinetic energy. Okay, kinetic energy will be sum of both of them, right? So kinetic energy 1 plus kinetic energy 2 for prismatic and for uh, revolute joint. So let's talk about link 1 first. So your kinetic energy 1 is half into m1 into d dot square, right? Link 2, your kinetic energy would be what? So link 2 has both translational as well as rotational energy. Both of them are there and we need to define both of them individually. So your Ke2 is half m2 v2 square plus half I2 theta 2 dot square. Okay, let's substitute v2 square because this is what we have already calculated. Okay, so we'll substitute it. So your Ke2 becomes half m2 d dot square plus r2 square theta 2 dot square minus, it is just what we have derived earlier, 2r2 d dot sine theta 2 into theta 2 dot plus half I2 theta 2 dot square. So your total kinetic energy would be summation of both of them, which would be half into m1 plus m2 into d dot ka square plus half into I2 plus M2 R2 square into theta 2 dot square minus M2 R2 sine theta 2 d dot theta 2 dot. Alright. Now, let's talk about the potential energy. So what happens? I've booked this room. But it is not booked. Like I booked it till 8. Okay, for potential energy, your gravity acts along the negative y. Okay, so link 1 has no vertical motion. So your potential energy for link 1 is 0. Okay, and for link 2, your height would be what? Sorry, y2 would be what? It was just r2 sine theta 2, right? R2, this is R2 and this component. So it's R2 sine theta 2. Alright. Then what is your potential energy? It is M2G R2 sine theta 2. So your Lagrangian here is L is equal to kinetic energy minus potential energy. If we expand all the terms that we have written, it would be half M1 plus M2. This appears to be a dot, just a second. M1 plus M2 d dot square plus half I2 plus M2 R2 square theta 2 dot square minus M2 R2 sine theta 2 d dot theta 2 dot minus M2 G R2 sine theta 2. Okay, so this is the Lagrangian that we have obtained by subtracting potential energy from kinetic energy. Now what is the next step that we need to follow? We need to formulate Euler-Lagrange equation. Alright, so let's write Euler-Lagrange's equation. Okay, and it is d by dt into dou L by dou qi dot minus dou L by dou qi is equal to qi. Okay, now how do we go about it? What was our q? Q was d and theta 2. Those were the generalized coordinates that we defined. Okay, so let's do this exercise first for d and then for theta 2. All right, so we'll do equation for d. Okay, so dou L by dou d dot is equal to what? We'll differentiate it with respect to d dot. All right, so for the first term, what do we get? We'll just be left with m1 plus, I'll just pull this here, m1 plus m2, and we'll have 2 out, 2 coming out, half would cancel that, and we would remain just with the theta d double dot, right? Am I writing it correctly or not? No, it would be single d. Okay, because it is with respect to d dot and we haven't yet taken d upon d dot. Okay, minus m2 r2, because this term does not have any d dot, so it would become 0. And then there is another term, this term only has d dot and the last term also does not have, so we'll work with the third term. It's m2 r2 sine theta 2 into theta 2 dot, right? Once we do that, we have to differentiate it with respect to time. It would be m1 plus m2 into d double dot. I hope everyone is able to catch up with what I am teaching. Like, it is a very basic question, and we are going end to end for this question. I did not go in detail for 2 hours because that is already discussed in the slides. But this is something that will give you a flavor of how do we deal with, or how do we derive the equations of motion using Lagrange's method. Okay, so how do we define the energy of the system, and then we define the Lagrangian, which is basically the difference between kinetic energy and potential energy. Then we use Euler-Lagrange's equation, and from there we try to derive the equation of motion. We'll be able, since it has two generalized coordinate variables, we'll get two equations, and that is how we're doing. All right. Okay. So what we'll get here, m1 plus m2 into d double dot minus m2 r2 into, now this term has to be differentiated with respect to time, and it has two terms, so we have to be very cautious here. Okay, so cos theta 2 into, let's keep theta 2 dot for now. Have I made some mistake here? m2 r2. Okay, so sine theta 2 a differentiation is cos theta 2, and then you'll get another theta 2 dot coming out, right? And that theta 2 dot is multiplied by theta 2 dot, so we'll have theta 2 dot square. Okay, plus will this time we will separate out sine theta 2 and differentiate theta 2 dot, so it would be theta 2 double dot. Okay, and del L by del D is equal to 0, right? Because we do not have any term related to just D here. We don't have. Do we have? We don't have in this complete equation. We don't have, right? So this term is directly 0 for when Qi is D, not for the other case. Okay. Okay. Now, so del L by dou L by just somewhere I am saying del, it is dou, and I'm just spelling it, so I should not do that. But yeah, but whenever I'm saying that, please assume it. Whenever I'm cautious, I'm correcting it. Okay, so from here what do we get? We get m1 plus m2 into d double dot minus m2 r2 into cos theta 2 dot square plus sine theta 2 into theta 2 double dot is equal to 1. Right? So this is our very important first equation of motion for dynamics for the prismatic joint and for this PR system. All right? I hope this is very clear. Now, so this was the equation that we have derived for D. Now we also need to derive, because you see here it is Qi. Qi has D and theta 2, both of them. We did everything for D up until now. We haven't done anything for theta 2. Okay, so we'll do for theta 2. So we'll do equation for theta 2, and it is del L upon del theta 2 dot, so dou L upon dou theta 2 dot is equal to, we need to differentiate the Lagrangian with respect to theta 2 dot. Where is our Lagrangian written? Here. Okay, we have to differentiate it with respect to theta 2 dot. So we'll take care of this term, we'll take care of this term, we'll take care of this term. No, we won't even take care of this term because it does not have theta 2 dot. Okay, so only these two terms would come into picture. So let's see that. So dou L upon dou theta 2 dot is I2 plus m2 r2 square into theta 2 dot minus m2 r2 sine theta 2 into d dot. All right. So from here, when you do d by dt, of this term, what do you get? You just have to do d by dt of the term that we have obtained right now. It's I2 plus M2 R2 square into theta 2 double dot minus M2 R2 cos theta 2. Again we'll apply the same thing, u into v wala rule. Cos theta 2 into theta 2 dot into d dot plus sin theta 2 into d double dot. Alright. So from here, your dou L upon dou theta 2 comes out to be minus M2 R2 cos theta 2 d dot theta 2 dot minus M2 G R2 cos theta 2. So what is the final equation coming from here? You have to equate, you have to put all of these here and then you have to equate it to the torque. Okay, because torque is your external wrench acting. So your final equation here is I2 plus M2 R2 square into theta 2 double dot minus M2 R2 sin theta 2 into d double dot plus M2 G R2 cos theta 2 is equal to tau 2. Okay. So this is your equation of motion that you get for theta 2. So what are your final equations of motion? One of them is this one, which is for prismatic joint. This is your second equation of motion, which is for revolute joint. Okay, so let's write it together and then we'll convert it into the matrix. Okay, so for prismatic joint, our equation of motion that we have derived is m1 plus m2 into d double dot minus m2 r2 cos theta 2 dot square plus sin theta 2 double dot is equal to f1. Okay, for revolute joint, what we have got, it's I2 plus M2 R2 square into theta 2 double dot minus M2, just a second, okay, so for the second equation it is M2 R2 sin theta 2 into d double dot plus M2 G R2 cos theta 2 is equal to tau 2. Okay, these are the two equations of motion. So if we want to write it in compact matrix form, which means MQ into Q double dot plus CQ Q dot into Q dot plus G as a function of Q is equal to tau. So what was our Q? Q was dm theta 2. So we have to do everything according to this. Okay. So what is your Q dot? It is just the derivative, and Q double dot, it is just their derivative. And what is our torque here? What is our tau? It's F1 and tau 2. These are the wrenches. Okay. So from here, can you find out what would be the mass matrix? Can you guys tell me what would be MQ, what would be CQ, Q dot, and what would be GQ? I think you should be able to answer directly. What would be gravity term? Can you guys tell me if you have done this. Basically, it is just these equations that we are supposed to manipulate in such a way that we can write it in the form of matrix, MCG matrix. So can you tell me what are these MC and G matrix?
MQ would be density and volume, D and V.
Sorry, uh, uh, density and volume. No, no, no. So what I'm saying is, see, this is the first equation, right? And this is the second equation. Now we have to arrange it in such a form that MQ matrix is there, which is being multiplied to Q dot, Q double dot. And what is Q double dot? If Q is this, then Q double dot is D double dot and theta 2 double dot, right? So what would be M matrix if it has to be, so can you take out theta 2 dot from here and D double dot from here? If you take it out, how would M matrix look like? It is just like, it is in completely expanded form. We need to get matrix out of it. It's just that. Okay. Similarly, for C term, you have to see what term is being multiplied with Q dot. That means what term is being multiplied with the vector which comprises of D dot and theta 2 dot. Okay. Okay. Has anyone come up with the final MC and G matrix? Can I get an answer from here? Should I wait or no one is going to answer? What is going to happen? Do you want me to wait if you're solving? Or should I give the answer? Like if I don't get any response, I'll definitely give the answer. But if you're solving, please let me know so that I can wait for 2 minutes or so. Else I'll move ahead. I Okay, okay. Yeah, I'm waiting. This is important. It's good that you solve it. You'll get a hang of it. I think Shravan was solving, but he got disconnected. And I don't hear replies from anyone else. So I think I'll go with the answer. Okay, so if you guys have not solved now, you can check this out. Uh, so your MQ matrix would be, it is just arranging these terms and nothing else, just arranging, okay? Your MQ matrix would be M1 plus M2 minus M2 R2. You understand it would be 2 cross 2 matrix, right? Because it has to be combination of both of the terms in Q. Okay. M2 R2 sine theta 2 and I2 plus M2 R2 square. Okay. C Q dot into Q dot is minus M2 R2 cos theta 2 into theta 2 dot square and 0. Okay. Then GQ is 0 M2 GR2 cos theta 2. Okay. And your torque is F1 into tau 2. Okay. So this is just compact notation for this. Okay. So in expanded form we just converted it into. So when you code now, when you want to solve these equations of motion in MATLAB or Python or anywhere, giving the equations of motion in this form is not recommended. You should always give them in the form of matrix, so that if matrix multiplication is required, addition is required, or inverse is required, the matrix calculations related to matrix can be done. Like if you expand it, you will be dealing it with every term algebraically, and it takes a lot of time and a lot of computation. But if you represent it in this way, it will always be helpful. All right. So this is the way how we go about it. Now after this, okay, let's move ahead. I think we did a whole problem end to end, how to arrive at the equation of motion. You could have also tried using this the Newtonian approach, by drawing the FBD and then trying to solve. But I think that would have been a more tedious process as compared to this. So because you are in total accounting for all the energies and then you are trying to find the equation of motion, it is less cumbersome, I think. So, okay. Okay, we'll go ahead with some questions and it would be very basic questions that we'll be dealing with. So if you know the answer to these questions, please write them in the chat box, or it would be nice if you can open up and speak, because on my screen I have this screen which you are seeing open and I don't frequently switch to the chat box. Okay, and I do have Meet small window appearing in screen picture appearing on my screen, but then most of the times I don't get any notification for the chats that you right over there. So it would be good if you can speak up by unmuting yourself. All right. Okay. So the first question is, the inertia matrix of a rigid body or a link is always positive definite, is always symmetric, is an orthogonal matrix. It represents the mass distribution in 3D space. Okay. So what is an inertia matrix? We already saw the whole definition, right? Where did we see it? My God, it's too before. Uh, okay. So this is the inertia matrix that we saw, right? And we saw how do we define IXX, IYY, etc. And how do we define IXY term. So it basically describes how the mass of the body is distributed in space. Okay. So our options are, okay, so our options are, it is always positive definite. So it's correct, right? Answer of question 1 is A and B. You are right, but partially right. Okay. So option D is also the correct answer. A, B, and D. Okay. Let's see why. So for this inertia matrix, uh, I think, hold on. Okay. Okay, so yeah, so it is definitely always positive definite, because we write rotational kinetic energy as half omega t I omega x, right? So energy always must be positive for any non-zero angular velocity. So we write it in this way, half omega omega
And what is
transpose.
the rank of inertia matrix?
Rank of inertia matrix, like all of them have to be defined, IXX, IYY. So it has to be, it is to be 3 cross 3 matrix, so rank should be 3. Okay, like we are only doing in x, y, and z direction. If you are doing in 2 dimension in planar motion, then you will not have all of them. You will have 2 cross 2 matrix only. Okay. Just
Okay.
yeah. I think someone has some question. Just got a pop up. There's a mock exam which I can end this at the end of the session. I cannot like answer all of these in the beginning, in the middle of the session. I'll try to see what you are saying. Okay. Okay. So what we are doing is, okay, it should be positive definite. That means so that our energy remains positive. Okay, you can never have negative rotational energy, thus the inertia matrix must be a positive definite. Is always symmetric is also correct. We already saw that IXY is equal to IYX, right? Similarly, IXZ is equal to IZX and IYZ equal to IZY, etc. This occurs because the integrals defining them are identical. Okay, so the inertia tensor is always symmetric, so I is always equal to I transpose. Okay, because it is symmetric, the eigenvalues are real, the eigenvectors define principal axis, etc. That is why we can diagonalize the inertia tensor. Okay, the third option is, it is an orthogonal matrix. Okay, it is incorrect. Why? Because for Orthogonal matrix means A transpose A should be equal to identity matrix, right? For example, our rotation matrix, if we talk about it, is identity matrix. But inertia matrix depends entirely, the entries depends on mass and geometry and not rotations. Thus, inertia matrices are not orthogonal matrices. So this option is wrong. All right. So rotation matrix is orthogonal, inertia matrix is symmetric. Okay. The fourth option is it represents the mass distribution in 3D space. So the inertia tensor tells us how mass is distributed. I should write this, I think. How mass is distributed relative to an axis. Okay. So, for example, if there are two rods with the same mass, rod concentrated near the center and there is some rod which is spread outward, they'll have different inertia matrices. Thus, inertia matrices encodes the 3D mass distribution. कि अगर कोई भी center point है, center line है, या फिर if you're fixing a point, if you're fixing a frame of reference somewhere, the way the mass is distributed around that point or around that line or anything is important, and that is given by the inertia matrix. So this option is also correct. Okay, so the final correct answers are it is always positive definite, it is always symmetric, and it represents the mass distribution in 3D space, and it is not orthogonal, it is not skew symmetric. All right, so okay, let's move to the next question. I hope this is clear. The Lagrangian formulation for obtaining the equation of motion of a robot requires the expression of the kinetic energy of all the moving links, the kinetic energy of all the moving joints, the difference between the kinetic and potential energy of all the moving links, the sum of all the kinetic and potential energy of all the moving links. Okay, so can anyone tell the answer? This is easy. We did a complete question on this.
Difference between kinetic and potential energy.
Very good. So it's the difference between kinetic and potential energy of the moving links. So the Lagrangian formulation is an energy-based method used to derive the equations of motion. So instead of using forces directly like Newton-Euler does, we use energy functions. So the Lagrangian is defined as kinetic energy minus potential energy. Okay, if there are n number of links, it's from 1 to n, and then we define, and then we apply the Euler-Lagrange's equation, which we saw in the form of differential equation. Okay, a differential and also the partial differentiation that we have, etc. All of these. So we define in this way. So the first option is kinetic energy of the moving links. Although kinetic energy is required, it is not sufficient, right? Lagrangian requires both kinetic and potential energy. So if we only use kinetic energy, what would we miss? We would miss the gravity forces. So a robot arm moving upward requires torque due to gravity, which appears to potential energy. The kinetic energy of all moving joints is also wrong because links have mass, inertia, velocity, etc. and all of the joints are only the constraints that connect the links. So kinetic energy is computed for links and not joints. So the thing is, in the third option, we have the difference between kinetic and potential energy of all the links, and that's correct. We already did a question. And the last one is sum of kinetic and potential energy of all the moving links. No, that is total mechanical energy and it is not the Lagrangian, right? So this is incorrect. So this is the correct option. Very good. Okay, so let's move to the next question, I think. Okay. So the Lagrangian formulation for obtaining the equation of motion of a robot takes into account the losses due to friction at all the joints. We talked about it, right? Did it include friction by itself or did we have to add it? Okay. It is modified to take into account friction at all the joints in an ad hoc manner after the equations of motions are derived. Is it true? Okay. The third question is only applicable to serial robots. We never saw this happening, right? And the fourth is does not take into account the external forces and torques acting on the robot. Which option do you think is correct? How did we learn to incorporate friction? Does anyone remember? No one is answering? Okay. Okay, it might not be clear enough. I'll just go through it. Okay, Lagrangian mechanics is derived for conservative systems, right? Conservative systems are systems where energy is conserved. Forces can be derived from potential energy. What are the examples of conservative forces? They are gravity, they are spring forces, etc. And what are non-conservative forces? They are friction, they are damping, they are air resistance. Okay, so these forces basically dissipate energy. So they cannot be represented directly using the energy functions. Okay. So the formulation that we had in which d by dt of dou L upon dou Qi dot minus dou L upon dou Qi is equal to tau I. This formulation does not inherently include friction. Therefore, friction must be added manually afterward. Okay. So the first option is it takes into account the losses due to friction at all the joints. No, because standard Lagrangian formulation does not include friction. Friction is a non-conservative force. Since Lagrangian mechanics is based on energy conservation, friction cannot be directly derived from the Lagrangian. So this statement is false. The second statement is it is modified to take into account the friction at the joints in an ad hoc manner after the equations of motions are derived. This is correct because when we have the equations of motion of this form, M matrix into Q double dot, I'm not writing it now completely, CQ dot plus G is equal to torque, we can add plus F, which can take where we can take into account the friction. So friction can be modeled as a viscous friction and Coulomb friction, both of them. So these are added artificially from outside, and that is the reason why it has been called here to be ad hoc modification. Okay. The third option, it is only applicable to serial robots. No. Lagrangian formulation can be applied to serial manipulators, parallel manipulators, mobile robots, multi-body systems. So for parallel robots, we simply include constraint equations and sometimes Lagrangian multipliers. So the method is general and not limited to serial robots. So it is also wrong. The fourth option is it does not take into account the external forces and torques acting in the on the robot. Okay, so external forces appear as generalized forces on the right hand side. This is the one. So for robots, this Qi is basically Ti only. So there are external forces which are explicitly included. So the correct option is it is modified to take into account friction at all the joints in an ad hoc manner. Any confusion here? I hope this should be clear. So Lagrangian naturally includes inertia, Coriolis forces, gravity, etc. But it does not include friction damping. They must be added later. Okay. Okay, let's move to the next question then. The Lagrangian formulation for obtaining equations of motion of a parallel robot involves the elimination of the loop closure constraint equations analytically, involves twice differentiating the loop closure constraint equations, involves use of Lagrange's multipliers, one for each constraint equation, involves use of Lagrange's multipliers, one for each degree of freedom. Does anyone have an idea what should be the correct answer? Okay, let's go one by one. So it's about Lagrangian formulation for parallel robot, right? So parallel robots contain closed kinematics loop. If you have seen the lecture, you might remember 4-bar linkage mechanism. They have closed kinematics loop. We also talked about Stewart platform the other day, right? So because of closed loop, the joint variables are not independent, right? Instead, they must satisfy loop closure constraint. What is meant by loop closure constraint? If there is a linkage, four-bar linkage mechanism, then they must satisfy this loop closure constraint. If we break from here, then it should be satisfying the constraints here. Okay. So mathematically, if you remember, we had done eta of q is equal to 0. So these are called holonomic constraints. For constrained systems, we modify the Lagrangian. And how do we do it? We use Lagrange's multipliers. So what do? We do like this. We define a Lagrangian, a new Lagrangian, which is the old Lagrangian minus the constraint equations. Now there can be some m constraint equations, let's say, and they are multiplied with Lagrange's multipliers into the constraints. Okay, so these are the constraint equations. Okay, and these are the Lagrange's multipliers. So why Lagrange's multipliers? They represent the constraint forces required to enforce the closed loop geometry. So each constraint equation needs one multiplier. So if we have m constraints, we would need m multipliers. Okay. Now, let's go option by option. It involves the elimination of the loop closure constraint equation analytically. Incorrect. In theory, you could eliminate constraints by solving them analytically, but in robot dynamics, this becomes extremely complicated. Instead, the standard method is to retain the constraints and introduce Lagrange's multipliers. Okay? Thus, this option is not the typical formulation used. Second option is involves twice differentiating the loop closure constraint equations. This is correct. Why? Because this is our constraint equation. We differentiate it twice. The second, okay, I don't know if you remember this. Okay, so the constraint equations are basically differentiated twice. Okay, so what would happen? Let's say our constraint equation is represented by this. We differentiate it once. Let's say we get some equation into q dot we would get, right, on differentiating once. If we differentiate it again, it would be psi q into q double dot plus psi dot in q into q dot is equal to, sorry, is equal to 0. So the second derivative is required to incorporate constraints into the dynamic equation. This is why the constraint equations are differentiated twice. So this is correct. The third option is it involves use of Lagrange's multipliers, one for each constraint equation, right? The number of constraint equations that you have, there are number of multipliers you'll have. So these multipliers represent constraint forces. So there is one multiplier per constraint force. So this is also correct. The fourth option is it involves the use of Lagrange's multipliers, one for each degree of freedom. So multipliers correspond to constraints and not degrees of freedom. For example, a mechanism may have 6 variables and 3 constraints. So degree of freedom is 3. Multipliers are 3. But this is not generally equal to degree of freedom. Thus, this option is incorrect. So the correct options are these two. Okay. I think you...
Where explain a term holonomic constant for my parallel manipulator.
Sorry, I do not understand.
Holonomic constant.
Yeah.
The Lagrangian formulation for a parallel manipulator takes into account loop closure constant equation as holonomic constant. Please
Yeah.
explain the term holonomic constant.
Okay. So you want to... Just a second. So holonomic constraint we define basically when our equation depends on q and q dot both. Just let me take an example. You want to know it for parallel robots? Just hold on. Okay. So what we'll do, so the first thing is, the very important thing is, In parallel robots, holonomic constraints arise because the robot has closed kinematic loop that we saw here. Okay. So these loops basically force the joint variables to satisfy certain geometric relation at all the times. Okay. So what do we mean by holonomic constraint? It is a constraint that can be written purely as a function of configuration variable, means a function of position. So if we have q or whatever it is, I'm not going into detail, but not these constraints depend on joint positions and not velocities. Now, do you understand holonomic and non-holonomic constraint for let's say a car? Is a car holonomic robot or a non-holonomic robot?
Holonomic.
Car is a holonomic robot. Why? Why would you say that? Like I'm not asking in terms of very mathematical side, but I'm asking why would you say that, let's say from your whatever you know from your learnings. So I'll make the things clear. A holonomic robot is one, let's say this is a point robot, okay? It can move in all the directions, right? It can move laterally, it can move forward, it can move in any direction as it wants, okay? But if you have a car, you cannot move sideways, right? You have to take a turn and move sideways, but your wheels cannot go sideways. So car is not a holonomic robot. It is a non-holonomic system. So a robot is holonomic if the number of independent control inputs equal number of degrees of freedom. That is something in configuration space. I won't go much into that. But the thing is, omnidirectional mobile robot is a holonomic robot. But for lateral movement, you need to consider the velocity as well. Here, velocity also comes into picture. It's not just about the position anymore. It is also about the velocity now. Okay. So a car cannot move sideways. Its wheels impose a no slip constraint, right? We cannot have the slipping of the wheels. So this equation involves velocities and not just the positions. That means that the constraints cannot be integrated into a pure position equation. Therefore, it is non-holonomic. Okay. Now, so from here you understand what is holonomic and what is non-holonomic, right? Now,
Okay.
after this, now it's about parallel robots that we were talking. So parallel robots have closed loop, as I said here. For example, there is four-bar mechanism or steward platform or anything. So there are number of constraint equations, and these constraint equations ensure that the loop remain closed during the motion. If these constraint equations are violated, it won't remain like that. And then there are a couple of calculations and everything. So the thing is, we here the holonomic constraints in case of parallel robot depend only on position q. They have nothing to do with velocity. They represent loop closure in parallel robots. They can be integrated into configuration constraint कि मेरा ये वाला जो link है इसका position should be equal to इसका position. And so because of all these reasons, this becomes a holonomic constraint because there is no restriction here in terms of velocity. It is in terms of position. It is in terms of coordinate. Okay. So if it is a 4-bar loop closure, it is holonomic. If it is wheeled mobile robot no slip constraint, we cannot slip sideways, then it is non-holonomic. So okay, so because we have closed kinematic chains, these chains actually reduce the degrees of freedom of the robot and so on. So holonomic robots constraints in holonomic constraints in parallel robots are geometric loop closure equations that restrict the positions of the joints so that the mechanism remains closed. All right. So there were two things. One is be clear what is the difference in between holonomic and non-holonomic, and the second thing is why it is important in parallel robots, just because we want to maintain the loop closure equation. All right.
Okay, ma'am.
Okay. So I think we were done with this question. If someone has any question related to this, if not, then we'll move to the next question. Okay, I think there are no questions. Let's move to the fifth question. The equations of motion of any rigid serial multi-degree of freedom robot contain a positive definite symmetric mass matrix, is a set of non-linear second order ordinary differential equation, contains Coriolis centripetal term which are linear in joint rates, cannot contain terms which are only function of joint variables. Let's go one by one. So the first option is it contains a positive definite symmetric mass matrix. I think we already saw this thing in the first question. So it is a symmetric matrix, it is a positive definite matrix. We are not going to details anymore. The second is it is a set of non-linear second order ordinary differential equation. This is also correct, right? We wrote mq double dot plus cq dot plus g is equal to torque. So robot dynamic equation contains second order because acceleration appears here. Okay. So, and it is non-linear because non-linearities appear due to trigonometric terms, velocity products, coupling between the joints, all of these. So we saw this type of thing, cos theta 2 into theta 1 dot, theta 2 dot and all of these. So ordinary differential equations, they involve derivatives with respect to time only. Thus they are non-linear second order ODEs. Okay. The third option is it contains the Coriolis centripetal term which are linear in joint rates. Coriolis and sorry Coriolis and centripetal terms are quadratic in joint velocities and they are not linear. Therefore, they are not linear in joint rates. And the fourth option is uh, cannot contain terms which are only function of joint variables. The gravity vector depends only on joint positions. Okay. So this gravity term GQ is basically MGL cos theta type and it only contains the joint position. So there is a term, right? So this is also wrong. So therefore the equation does contain terms that depend only on joint variables. So these two are the wrong answers. Okay. Any confusion here? If not, we'll move to the next question. Okay. So let's move to the next question. So the general forward dynamics problem in robotics is stated as given joint trajectory. So it is just talking about forward dynamics and we directly know that what happens in in forward dynamics. If joint trajectory is given and joint torques agar nikalna hai, so it is an example of inverse dynamics. Right. This is wrong. So, and what is, so this is directly inverse dynamics. So we vote out this option. Okay, because a motion is given and we are computing the torques. The second option is given joint trajectory as a function of time, obtain maximum joint torques and forces. Why? Still it is an inverse dynamics problem. It only adds the words maximum, but the input is still trajectory. So it is also wrong. Forward dynamics does not start from trajectory. The third option is given external forces and torques acting on the robot and the joints, obtain the joint trajectories as a function of time. This is correct. Because we are given the torque and we want to solve for QT, thus we compute how the robot moves when the forces are applied. If we apply certain torques from motors, the robots will move, what trajectory it is going to follow, all of these constitute the forward dynamics. So this is correct. Option 4 is given the external forces and torques acting on the robot and the joints, obtain the maximum acceleration at the joint. No, this is incorrect. Forward dynamics does not compute only maximum acceleration, it computes the complete motion over the time. It computes QT, Q dot T and Q double dot T. So this option is incomplete. That is why this is also incorrect. Okay. Any question with this? No question? We'll move to the next question. Okay. The Lagrangian multiplier introduced in obtaining the equation of motion of a parallel manipulator can be used to obtain the constraint forces at the joint. First of all, why do Lagrange's multiplier appear? Because we have the constraints. Parallel manipulators contain closed loop, example 4-bar mechanism, etc. Right? We saw that constraints appear as this. To enforce these constraints in the Lagrangian formulation, we introduce Lagrangian multipliers. We also saw this, that we can write it as lambda j into all the constraint equations where this j varies from 0 to 1 to some m constraints. So the thing is, it can be used to obtain the constraint forces at the joint. The multipliers lambda correspond directly to constraint forces, thus they can be used to compute internal forces in links, reaction forces, joints, and constraint forces, all of them. This is very useful in the mechanical design, right? So this is correct. They are related to a torques and force at the joints which do not work. Constraint forces do not perform work. That is true. The reason is the motion of the system always satisfies the double differentiation of the constraint forces. So the constraint forces do zero work, and this is the fundamental property of the ideal constraint. So this is also correct. Okay. For example, if there is a hinge joint, the hinge reaction force prevents motion in certain direction but does not produce any work. Okay. The third option is, are mathematical entities which have no physical meaning. Although they arise mathematically, they have a clear physical interpretation. They represent constraint forces, reaction forces at joints, all of them. Thus, they are not purely mathematical artifacts. So, this is wrong. They are typically constants. Lagrange's multiplier depend on configuration, Q, Q dot, and Q double dot. Thus, they vary with time. They are not constants. So, this is also wrong. Alright. I hope this is clear. Any confusion in this question? No? If not, then we'll move to the next question. We just have 12 questions, so it's 8 and we'll have 4 more. And we are going fast, I think, so we'll be done. So the non-holonomic constraints are similar to the loop closure constraint equations, cannot be incorporated in the Lagrange's formulation, require single differentiation, and are not integrable function of joint variables and joint rates. Okay, so the concept here is holonomic constraint only depends on the configuration variables and not on Q dot. Loop closure is now in a 4-bar mechanism, equation you know already. These constraints can be integrated and expressed purely in terms of Q. If there are non-holonomic constraints, they also depend on Q dot. Okay, and they cannot be integrated into a function of only Q. Example, mobile robot wheel constraint, as we discussed right before this. So if we talk about the option, they are similar to loop closure constraint equations. Now, loop closure constraints are holonomic constraints. We already saw they depend on the position variables. Example is this one. So non-holonomic constraints depends on velocity, so they are fundamentally different. So this is incorrect. The second option is it cannot be incorporated into the Lagrangian formulation. They can be incorporated, but in a modified form. Non-holonomic constraints are, so I won't go into the details, but they can be written as phi t plus psi q into q dot is equal to 0. Then the Lagrangian equation are modified using the Lagrange's multiplier, so they can be included, and this is also incorrect. The third is it requires single differentiation. So the holonomic constraints require two differentiation when deriving dynamics. So differentiate once and you get velocity constraint, differentiate twice, you get acceleration constant. So for non-holonomic constraint, the constraint already appears in the velocity form. Thus, only one differentiation is required to obtain the acceleration relation. So this is correct. The fourth option is they are non-integrable function of joint variables and joint rates. That is actually the definition of non-holonomic constraints, right? We already saw. So they depend on Q and Q dot both. They depend and they cannot be integrated into a function of only Q. Thus they restrict the velocity space but not the configuration space. So non-holonomic constraints restrict motion, directions, not positions. Okay. So these both are the correct answers. I hope it is clear. Okay, let's move to the next question. The inverse dynamics of a serial robot involves obtaining joint torques and forces for a given joint trajectory. This is correct, right? Inverse dynamics की बात हो रही है. So We obtain the joint torques and forces from the trajectory. The second option is, can be solved by substitution in the right hand side of the equation of motion. Yes, it is correct. And why it is correct? Because inverse dynamics is very straightforward mathematically. We already know q dot, q double dot. We substitute them and there is no differential equation. So in this equation, torque is equal to mq double dot plus cq dot plus g. इसमें we can substitute this, we know, we can substitute them directly. There is no differential equation needed to be solved. It becomes a direct algebraic contribution. Okay, so this is also correct. So that is why inverse dynamics can be computed very efficiently. Then the third option is require solution of a set of ordinary differential equations numerically. No. Solving ODEs is required for forward dynamics, not inverse dynamics. So this is wrong. Okay. And so this is basically forward dynamics. And the fourth option is, it requires solution of a set of differential algebraic equations. So differential algebraic equations appear in parallel robots where constraints exist. Serial robots do not produce these differential algebraic equations. Thus, inverse dynamics of serial robot does not require this. So this is also incorrect. Okay. Any confusion here? Let me check the chat box once. Okay. Okay, I think you guys are answering in the chat box, but I'm not able to see it, so that's fine. Let's move to the next question. The question is, the equations of motion of 4-bar mechanism is one ordinary differential equation corresponding to its degree of freedom. Although the mechanism has 1 degree of freedom, we typically derive equation for all the moving links before applying constraints. Thus, the formulation initially produces 3 ODEs. So this is wrong. The second option is, there are 2 ordinary differential equations and one algebraic constraint. This is also incorrect because we have 3 differential equations and 2 constraint equation. I won't be able to take you. I think we can discuss it in the next class if needed, but I would like you to figure this out. The third option is, there are 3 ordinary differential equations and 2 loop closure constraints. This is correct, as I said here. And the fourth option is, there are 4. No, this is also incorrect. So it has 3 differential equation and 2 constraints. I want to write the solution, but I don't think I have sufficient time right now. But what we can do is, it only has 1 degree of freedom actually, and then we initially obtain 3 differential equations and then 2 loop closure constraints, etc. So okay, I want you guys to have a look at this question on your own, okay? Because I won't be able to go into detail, I think, right now. If there is any problem, we can look at it in the next class, okay? Okay, next, let's move to the next question. We just have 2 more questions remaining. The state space form of the equations of motion for n degree of freedom robot is what? So, if let's say q is q1, q2 up until qn, we convert it into a state space because we want to apply ODE 45 and Runge-Kutta methods. So we define the state variables. So the state variables has 2n. Why it has 2n? Because it is q1 to qn and then it is q1 dot to qn dot variables. Okay. And so the first is, it has n first order ordinary differential equation. It is incorrect because there are two n state variables. Each joint contributes the position and velocity both. So we need 2n. Okay. And the second option is 2n first order ordinary differential equation because each joint contributes 1 position state, 1 velocity states. Thus total state is 2n. Okay. So this is correct. The third option is, there are 2n second order differential equation. We originally had n second order equations. After state space representation, they become first order equations and not second order. So this is also incorrect. And linear equations, no, we do not have. Robot dynamics equations are non-linear and they are not linear equations. So non-linearities, as we saw, come from trigonometric terms, velocity products, configuration dependent inertia metrics, etc. So not like that. Okay, I hope this is clear. Any confusion here or this is clear? If it is clear, then we'll move to the next question. This is the last question that we are covering for today. The recursive Newton-Euler algorithm can be used to solve what? Inverse dynamics, forward dynamics with what complexity? Okay, it's for serial and parallel robot both with the same complexity. So, robot dynamics can be derived using Newton-Euler formulation, and there are two other methods which I am not saying right now. So, for inverse dynamics, we have QT, Q dot T, and Q double dot T, right? So, the algorithm has two passes along the robot links. One is forward recursion, and the second is backward recursion. All of these are happening. So, my point is complexity is only due to the number of links. If the number of links is n, the order of complexity is n, that is for sure. The first option is the inverse dynamics of a serial robot has complexity of n, complexity of order of n. So, recursive Newton-Euler algorithm is specifically designed for serial manipulators and inverse dynamics. So, this is correct. And it runs in linear time, which is order of n. The second option is the forward dynamics of a serial robot has the order of complexity as n. No, this is forward dynamics and it requires matrix inversion or for special algorithms So the Newton-Euler algorithm is not used for forward dynamics directly. Why? Because what do we do here? We have MQ double dot, which is MQ double dot and torque minus CQ dot minus G. So it requires the matrix inversion, right? So this Newton-Euler algorithm is not designed for this. The third option is the inverse dynamics of the parallel robot. Parallel robot contains closed loop. It has constraint equation. The recursive Newton-Euler algorithm is designed for open chain serial robots and not parallel manipulators. So this is also wrong. The fourth option is the forward dynamics of a parallel robot and has this complexity. Okay, the parallel robot dynamics involve constraint equations and differential algebraic equations. So even it is as wrong as it was for the inverse dynamics option. So this is also wrong. So the only correct option is the inverse dynamics of the serial robot has the complexity of order n. All right. Okay, I think this was the last question. We end here. And one more thing is, so what do we have in the next class? We have motion planning and linear control. Please look at control systems lecture. Have basic knowledge of controls, PID control and everything. Also watch the lecture by Professor Ashita Ghoshal that is already scheduled for you to watch. It's on motion planning and control of single link and control of multi-link serial manipulator only. It would be, I think, easier one. So please go through it before you attend the next class. It would be only helpful for you if you go through it. And if anyone has any question that needs to be clarified, please ask me, else we can end the session. And I think Yagnesh had asked me a question, but he's not on call. So I think I won't be able to answer it. Anyway, it was something related to AI, I think. Okay.
Thank
Okay.
you, ma'am.
Yeah. So I think no one has any question. We'll end the session and we'll meet on next Monday at the same time, 6 to 8 p.m. Till then, bye.
Okay, good night, man.
Yeah.